Hello, in this video I'm going to talk about the Big Bang Theory and the evolution of the universe. So the Big Bang Theory, this was established in the 1930s and it describes the origin and the evolution of the universe. And we've already touched on this in some previous videos, notably the one on Hubble's law. We had Edwin Hubble in the 1920s getting this first evidence that the universe is expanding. He was looking at these distant galaxies and the redshifts in the spectra of these galaxies, seeing that they're moving away from the Earth. And whatever direction we're looking at, everything is moving away, due to the expansion of space. And the suggestion from this is that, well, if we're going forwards in time and everything's expanding, if we go back in time, everything will be contracting, and we can keep going back in time until everything has contracted down until a single point. Now, that isn't a conclusive argument of that must have been what happened in the past, but it's certainly logical. And the models that have been built off of that certainly match the observations that have been made in the last century or so of what's happening in space. This has allowed then, as we did in that video on Hubble's law, to make a first estimate of the age of the universe. We made a calculation that came out at around about 14 billion years, depending on which value of the Hubble constant we were using. People tend to use around 13.7 billion years, around that, for our best guess at the age of the universe nowadays. But yeah, this was all coming together in the 1920s, and then the theory was established in the 1930s. Now, we gathered a lot more evidence over the last 100 years or so, and the theory has then spawned various models of how the universe has evolved, and these are continually changing. This is far from nailed down, because there's a lot of new discoveries happening in this area, none more so than dark energy, which I'll mention later on, and of course there's still the unknowns around dark matter as well. So there's a lot of stuff that's still being figured out. But the most notable piece of additional evidence, aside from Hubble's discoveries about the expansion of the universe, the most notable additional piece is going to be the cosmic microwave background radiation. So this was first detected in 1964, and it's a uniform microwave signal that can be detected in all directions in space. And this is a remnant of the Big Bang, or at least not long after the Big Bang. So it's predicted by the models built around Big Bang Theory, and it's been observed. So we've got a nice matching up there of predictions and observations. And there's two main ways really of describing the origin of this microwave background radiation. So both of them start off in the same place. We're talking about a very hot early universe. We've got everything that's in it now in terms of matter and energy condensed down into a much smaller space. So it's going to be very hot, very dense, a lot of energy there. You've got a lot of high energy photons, lots of gamma rays that are zooming around all over the place. So we've got lots of high energy photons. So what is actually happening here? So if we're thinking of it in terms of high energy photons, then we can say, well, the expansion is going to lead to effectively a redshift of these photons. And according to all of the models that we've got, and then the observations that matches with this, is that the redshift will take these into microwaves, from gamma waves into microwaves. So that's one way of thinking of what's happening with the expansion in terms of the wavelength of these photons. Of course, the other thing is to look at the temperature. So it's very hot. So if you've got something that's very hot and you've got an expansion, then we're going to get cooling. And we can model the universe as a black body in the same way as we did with stars. So if we were going to look at our displacement law, Wien's displacement law, in the way that we do with stars, and see, well, what is our lambda max for this stage in the universe's evolution, and then how does this match up with our observations? So we're getting a lambda max of around about 1 millimeter for a temperature now of 2.7 Kelvin. This is the temperature of space, and this is the peak wavelength of a black body of that temperature. and this again is microwaves. So we've got a nice connection here, a nice match up between the predictions and the observations. So this is giving more confidence in at least some parts of the models of the evolution of the universe. Now, there's been more observations on the background radiation, because if we're going to start getting clumping of matter, as in we're going to get stars and we're going to get galaxies, then we can't have just everything being completely uniform. There needs to be some kind of ripple going on so we can get clumping of stuff. And this is what experiments, I mean, you've got things like the Planck mission, which was 2009, 2010, something like that. So the Planck mission was then mapping out the background radiation and looking for any kind of variability. And this is what we're seeing in this picture here. So you've got some hot spots in the red and the yellow, and some cool spots in the blue and the darker blue. And these variations are very, very small, but they are variations nonetheless that were the seeds for star formation and galaxy formation. So again, this is just fitting in to big chunks of the models that are built around the Big Bang Theory and giving more confidence that this is actually what has happened in the evolution of the universe. So while I'm on the evolution of the universe, so I'll come back to a bit more evidence for the Big Bang in a moment, but I'll break off just to give a bit of a timeline on this. I'll go to another slide, I think, for this. I mean, exact times are hard to pinpoint on all of this, and there's a lot of speculative stuff that goes on, particularly in the first second of the universe. Obviously, it's very difficult to be certain about anything that's happening in the first second of the universe. We're going back 13.7 billion years, but the models are telling us certain things. So just to get a flavour of what's happening here from the beginning up to the present day, we're starting with energy and not matter right at the beginning. And we need to then get this conversion of some of the energy into matter. And this is what's happening in the first second. Now, the idea is that all of the matter was created in this first second. But we start with this period of what's called inflation, which is a very brief but enormous rate of expansion in percentage terms right at the beginning of the universe. So we're talking here about crazily short time into the start of the universe, 10 to the minus 35 seconds, and you get this massive bit of expansion. Quite often when you see these pictures of the evolution of the universe, you'll get the Big Bang, and then it will balloon out into these sort of trumpet shapes. So you're seeing this sort of thing going on where they're drawing it. It's a bit like a trumpet, and they draw, this is time going off left to right. And this big expansion here, this is the inflation part right at the start of the universe. This isn't all entirely at scale. It's impossible to get it all at scale. So, unless you've got it on some kind of log scale. But you get this inflation of massively expanding the amount of space in percentage terms. And then you're starting to get matter to form. So around 10 to the minus 6 seconds, we start getting quarks and leptons. And then still within the first second, maybe 10 to the minus 3 seconds, we're going to start getting protons and neutrons. So we're getting some matter coming out, but it's all in some kind of plasma type form. Everything's ionized. It's all really, really hot. All of these gamma photons that I was talking about in terms of the microwave background, they're not able to escape this sort of mass of energy and matter. So this is when people talk about the universe being opaque. So this isn't the origin of the microwave background. That is going to come later when we start getting matter forming, atoms forming, I mean. So when we get to around about 100 seconds, we're going to start getting nuclei. So more than just, I know a proton is the nucleus of a hydrogen atom, but we're going to start getting things like deuterium nuclei, helium nuclei, a little bit of lithium, beryllium maybe. So we've moved on to about 100 seconds. But in terms of actually getting atoms, for it to be cool enough for atoms, you're looking at about 400,000 years. And this is where it's cooled down cool enough that we're going to get atoms. This is when the universe then becomes transparent. So the photons that were around at this point, this is going to be where we're getting the origin of our cosmic microwave background radiation. So that's what we're looking at being redshifted or cooling down from that point. Then we're getting into very big jumps. Yeah, you can see, I mean, these are already huge jumps. We've gone from 1 second to 100 seconds and then to 400,000 years. Then we're going up to the first stars at, say, 200 million years. I mean, I see textbooks pick out wildly different numbers on this. Some of them go as low as 30 million years. Some of them are going 300 million years. I mean, it's a huge variation. But let's stick it around 200 million years. These numbers, you don't have to be that exact with them. It doesn't really matter. It's just a long time after these other things happening. Then 800 million years, you might get, say, the Milky Way. That's what we're thinking for the birth of the Milky Way, our own galaxy. So you've got galaxies forming. Then we're getting into the billions. 9 billion years, as we were saying in the section on the sun and the planets. So 9 billion years, we've got the solar system. So that is a long time afterwards. 10 billion years, we've got the Earth. Then 11 billion years, we're getting life on Earth. So, but that is just life as in the very, very earliest life, where we're getting cells and things like that. We're a way off. If we're getting to 13.7 billion years now, I mean, that is essentially when humans came into existence. Humans were only looking at, say, 200,000 years for Homo sapiens to be wandering around on Earth. So 200,000 years. I mean, we've got 13.7 billion. So if you're going to take off 200,000, what's that? 0.0002, if I've got my decimal places right there. So, I mean, it's not even made a dent in 13.7 billion years. So, we are right at the end of all of this. I mean, it's blink of an eye compared to everything else that's happened in the evolution of the universe. But yeah, it's useful to have a general idea of what's happening in timescales. But really, you're looking at matter being created in the first second, then it's cooling down over a few 100,000 years to get atoms. So this is a useful sort of number, this 400,000 year one, where we're getting the microwave background. And then we're getting into millions for stars and galaxies and billions to get to a solar system that we're actually in. So yeah, it's just mind-boggling. I mean, these numbers are so extreme, it's hard to know what to do with them, really. So having set up that timescale, let's look at another bit of evidence then for the Big Bang. And this is nucleosynthesis. So the models that we got make predictions about the relative abundances of different elements, different atomic nuclei that are formed in the early universe. So, we just spoken about this on the previous slide. After 100 seconds or so from the formation of the universe, we're getting atomic nuclei beginning to form. And then up to when we get to 400,000 years, that's when we're getting atoms forming. So we've got this time in the early universe, we're getting these nuclei. We've got deuterium, helium, lithium, beryllium, these sort of things. And the models are predicting how much we've got of each one of these. This is what's called the primordial abundance of each one of these elements. So if we can take these predictions for the primordial abundance of, say, helium, and then compare that to observations now, then maybe we'll get another tick in the box for our Big Bang theory. There is, of course, an obvious problem with this, that we're talking about abundances of helium and other elements pretty much at time zero for the universe, and we're looking at things 13.7 billion years later. And we know that lots of things have changed. So just focusing on helium, okay, we've got the starting amount, we've got our primordial amount of helium, but we've created more by fusing hydrogen to create helium. That's all going on in stars. But we've also lost some by fusing helium into heavier elements. So how do we unravel the changes over the last 13.7 billion years from what it actually started as? So this is not an easy thing to do. So we need to if we're observing anything to do with helium, we need to have stars around, really, because if we don't have some stars around, we're not going to have something we can look at. Okay, stars themselves are very easy to look at, but then you've got and make observations of and look at spectra and things for relative abundances. But you've also got nebulae, and if you've got a big gas cloud filled up with hydrogen and helium, say mostly, okay, there's going to be other stuff, but you've got lots of hydrogen and helium in a nebula. If you've got a nebula with no stars, none of this is going to be ionized, and it's going to be very hard to actually observe any of it. Of course, if you've got some stars in there, then it's going to ionize this nebula. We get what's known as an H2 region. We spoke about these before. Remember, the 2 here is referring to the ionization state. So H1 is neutral hydrogen, H2 is ionized hydrogen. Obviously, that's as high as it goes for hydrogen because there's only one electron you can ionize out. So these H2 regions, these ionized nebulae, these are good places to look in order to see the relative abundances of hydrogen and helium. But we don't want to just look at any old H2 region because we want to have ones that have changed as little as possible. So we want to have ones that have got fairly small stars in, cooler stars that are burning much more slowly. We looked at this in the evolution of stars. If you've got really massive, really hot stars, they've got shorter lifespans, and they're also, they're converting the elements around. They're doing a lot more fusion. They're creating a lot more in the way of heavy elements. So if we can have the smaller, cooler stars, which just do that slow burn fusion for ages, well, we're barely getting any heavy elements at all. Okay, we're getting some hydrogen into helium, but that's happening slower than it is in the hot stars. Then at least we've got less change. So we want to go to these H2 regions, find the ones that have got as little carbon, nitrogen, oxygen as possible, and then start making some observations there. And it turns out that these regions that we're interested in are in dwarf galaxies. So there's a lot of dwarf galaxies around. Again, we spoke about this in the galaxies video. There are dwarf galaxies that are satellite galaxies to the Milky Way, our own galaxy. So if we can look in those, and they're much more primitive, there's less mass, there's less going on, there's less fusion, we can look at these H2 regions and then look at the emission lines. So we can look at the emission lines of hydrogen, helium, lithium, whatever, nitrogen, oxygen, look at all of these, see that there's not much nitrogen and oxygen, and then look at the hydrogen and the helium, well, and the oxygen as well. I mean, it's still going to be there, but it's going to be lower than in other H2 regions. And we want to then start making comparisons, because if we then plot the based on the strength of the spectral lines on observing the H2 region, so we observe the H2 region, we get our spectral lines, emission lines, absorption lines, we're going to have a whole load of things going on, and we compare the relative concentrations of, say, helium and oxygen. So we can plot these out. So we'll have some kind of concentration of oxygen, concentration of helium. We do this for a whole load of different H2 regions in, well, maybe the same dwarf galaxy or different dwarf galaxies. Plot these out and you're going to get some kind of scatter which has a relationship in it. We can then extrapolate back this to 0 oxygen, because in the early universe we didn't have any oxygen. It was all hydrogen, helium, and a little bit of lithium, beryllium. But we're extrapolating back to say, well, let's get rid of everything that's happened in stellar fusion, go back to where there was no oxygen. What is then our abundance of helium when we've got no oxygen? That's giving us an estimate of our primordial abundance of helium. And turns out that these match pretty well. These observations and then the calculation of our primordial abundance of helium, that matches well to the predictions from the models built around the Big Bang Theory. So it's another good bit of evidence for the Big Bang. So there's a lot of good evidence supporting the Big Bang Theory. But as I mentioned earlier, yeah, there's still a lot of unanswered questions. I mean, I went through some of these in a previous video on dark matter. Yeah, there's a lot of matter in the universe. We don't know where it is. We don't know what it's made of. So we've got that problem just in terms of, maybe 80% of the actual matter is not visible to us. It's dark matter. And then, of course, we've got dark energy, which came onto the scene in the late 1990s. And that's another big unknown. I mean, up until that point, when dark energy got discovered and the observations were supporting the existence of dark energy, most of the discussion was around whether the universe was open or closed. So what was meant by that was we knew that the universe was expanding, and so you've got an expansion going on, but you've got all of the mass in the universe is pulling everything back together. So it's slowing that expansion down. So what's then going to happen? Is there enough matter that the expansion will slow and then everything will start contracting again if the force due to gravity is strong enough? And that was the idea of a closed universe, going back to a big crunch. Or is it just going to slow down the expansion, but it will just either keep on expanding or just expand down to a stop, like an asymptote? And these were open universes. So that was the discussion really up until dark energy came onto the scene. And then with dark energy, this was based on observations that were suggesting that actually the expansion of the universe is accelerating. And this was, mind-blowing, really. And it raises the question of, well, what is driving this acceleration? And the answer that was given is dark energy. I mean, no one really knows what this dark energy is, but there has to be something driving this acceleration of the expansion if that is what is happening. And that is what people are trying to figure out when it comes to dark energy. And there's different models built around this, predicting different things. A lot of people say that this acceleration of the expansion started about 5 billion years ago. Some people say it will continue. Some people will say it will stop. There've been discoveries only in the last month or so which seem to have put the possibility of a big crunch and a closed universe back on the table again. So this is a fast-moving area, at least in terms of physics, of people trying to figure out what's actually happening with dark energy. So yeah, there's a lot of work that's being done in that area. I mean, dark matter and dark energy. I mean, there are Nobel prizes are begging here for people to figure out what's happening with all of this. So yeah, there's a lot of stuff that we're confident of inside the Big Bang. The idea that there was one, that there was this starting point for time and space at the Big Bang, how these elements were synthesized in the early universe, how stars and galaxies began to form. All of this is fitting together quite nicely, but there's still a lot of stuff to be worked out. So yeah, interesting times, and a lot of this stuff gets covered in undergraduate physics at university. So it's a very popular area of physics and astrophysics.